So in the previous lecture, we have learned how to use projection operator to estimate the symmetry adapted linear combinations out of a given set of atomic orbitals. So now that we know how to construct SALCs, now let's see how do we use these SALCs to develop the wave functions to describe the chemical bonding. So before we actually do that, let us have a slight refresher on what is chemical bonding and all. So let's start with lecture 35, and we'll be trying to understand the relation between symmetry and chemical bonding. So we are well aware of that atomic orbitals possess certain symmetry, right? That is, they can form bases for a given irreducible representation, IR representation, under a point group. Now, point group will be dependent on the molecular shape. So also when we know that if two atoms, so this is, let's say this is atom 1 and this is atom 2, when two atoms are combining to form a chemical bond, this is my chemical bond. So symmetry plays a great role here. Symmetry plays, we will see how, in establishing what interactions will take place and what will not. Okay, so we will see how symmetry comes into this picture, but symmetry has a great role in forming the chemical bonds. Okay, so this is what we already know. I'm not telling anything new. This is all we already know. So what we will be going to use is that symmetry and group theory can be rigorously used to construct appropriate wave functional description of the bonding in the molecules. Okay, so this we are going to see how to do that. And what else we can do using this theory, we can use construct hybrid orbitals that are helpful in reconciling the molecular shape. For example, YCH4 is tetrahedral and so on. So we will see that. So hybrid orbitals will be constructed with the atomic orbitals. For example, 1s and 3p orbitals combined to give a hybrid 4 sp3 hybrid orbitals that are oriented along tetrahedral geometry in carbon CH4, right? Hybrid orbitals that are available for bonding. So we will also see construction of, that will come later, but not in this lecture, construction of molecular orbitals for the entire molecule. So in general, we know that. So again, this is just a refresher. I'm sure you all know this. In general, the bonded state can be described by the famous Schrodinger equation, H psi equal to E psi, where we all know this. H is the Hamiltonian, psi is the state function and the eigenfunction, and E is the energy of that particular state, right? So now we can solve this equation for simple molecules like H2, but typically it is not easy and straightforward to solve, to first set up it correctly for more complex molecules, and then solving is another step which is not possible for, because it is very very difficult to invoke all sorts of interactions in a molecule. So typically what is done is, it is I will write, it is customary to construct approximate wave functions for the molecule from the atomic orbitals, right? So we use the given atomic orbitals and we construct the molecular orbitals from those, and from the atomic orbitals of the interacting atoms, we can say. So what happens in this approach, if two atomic orbitals combine in a constructive way, we can say that the result is buildup of electron density. So atomic orbitals are described by wave functions. So wave functions have positive phases and negative phases. If two positive phases are going to interact, there would be a, it's like simple addition of waves, right? So there would be a enhancement of electron density in that area. If two opposite phases of atomic orbitals will interact, then there would be a loss of electron density, and the corresponding interaction is called as bonding and antibonding, right? And if there is no change in electron density upon combination of atomic orbitals, then it is called as non-bonding interaction, right? So we'll see that how it works out. So the extent of, let us, the extent of overlap of atomic orbitals of, let's say, atom A and B. So nature and effectiveness will depend on the extent of overlap, and thus we can say nature and effectiveness, or the strength, we can say, of their interaction is given by Slater overlap integral. So what is Slater overlap integral? It is defined as S, then the integration of psi A, where psi A is the wave function describing the atomic orbital of atom A, and psi B, and over d tau. Of course, there is going to be boundary conditions and all. So now we can say that if S is positive, then the overlap results in bonding interactions, which is again characterized by buildup of electron density. If S is negative, it is antibonding interaction. And if S is equal to 0, it is possible, right? Then it is non-bonding interaction. So now, to understand this, let us actually draw the balloon diagram of these orbitals, which will help us understand how this works out, how the bonding and anti-bonding and non-bonding interactions work out. So let me just draw first the balloon representations. The first is the s orbital. So s orbital is typically drawn like a sphere. Let's call this as, and then it will have a positive phase altogether. All through it will be positive phase. So remember that this is a wave function. The wave functions will have plus phase and minus phase. Then we have, let's say, px, py, pz orbitals. So this is my x, y, and z, and then I'll call it as plus and minus, right? This is px. So I'll write it as px. Similarly, I can have py, balloon diagram for py. So then you'll have x, y, z. So in some books, you will see that the positive and negative phases of these lobes are different colors basically. So you will see that positive is shown in dark phase, dark color, or negative is shown in dark color, or either way. Or in some books, you will see just the plus and minus, because these are basically just the phase of this wave functions, right? So similarly for pz, we have x, y, z. You will have plus and minus. While we are doing this, let us also quickly draw for, just to remember, for all 5D orbitals. So for x, y, minus x, minus y. So I'm drawing this. So z is coming out of the plane of the board, so I'm not drawing z axis here. So the lobes are going to be in between the axis, and this is positive, this is positive, negative, negative. Okay, so this is dxy. Then you have yz, right? So we can have yz like this, minus y, minus z, and again this will be in between. So it is very easy to see that which lobe will be positive. The positive side of the two axes, if these are multiplying, this will give you positive sign. The two negative sides, if they are multiplying, they will give you positive sign. One negative and one positive, this will give you negative, because the multiplication is negative, and then so on, right? So this is just a simple thumb rule. This applies for everything. So here, positive side of x-axis will be positive, negative side of x-axis will be negative, and so on and so forth. So also draw it for xz, xz minus x minus z. Again, this will be minus. And now let's also draw for the rest of the 2D orbitals, which will be the dz square. And then there is a ring of negative phase over here, like this. So you have negative here and positive here. This is called as dz square, and the actual functional form, if you want to write in terms of Cartesian coordinates, you can also write it as 2z square minus x square minus y square. Okay, so for the calculation purposes, it is taken like this. I mean, it is taken in the complete form. This is x, y, z. Okay, and for x, y, z, the last one is t x square minus y square, which will be along the axis now. Now this will be, x will be positive, y will be negative, right? Because we have y square as negative, x square as positive. So now that we know how this works, let us try to see different bonding interactions. So bonding where S will be greater than 0. And then let's also look at the corresponding antibonding where S is less than 0. Okay. Now let's say that our interaction is between 1s and 2pz. So positive side, negative side. This is 2pz. This would be called as sigma. And if my S is interacting from the other side, you have negative, positive 2pz, 1s. This would be called as sigma star, right? You must have seen that in when you describe the bonding pictures. So bonding formation, bonding interaction, anti-bonding interaction. Okay. So now let's also see, let's say if you have dx square minus y square and 2px. So dx square minus y square will look like this, where we have positive side that is x and negative side that is y. So this is dx square minus y square, and you have 2px. So this will be sigma, because now there is a buildup of electron density over here when you combine these two orbitals, these two lobes over here. Whereas if you do it the other way around, this will be anti-bonding, right? Plus, plus, minus, minus, and you have negative, positive. So this will be sigma star. 2px 3dx square minus y square. Okay. So similarly, these are sigma and sigma star. These type of interactions are basically, we can say that these are symmetric with respect to, I can write it here, symmetric with respect to C2, collinear with the internuclear axis. Nuclear axis. So that is, if you pass an axis through this is my internuclear axis, and you do a C2 operation, this will be symmetric, right? So sigma sigma star interactions are symmetric with respect to C2, which is collinear with internuclear axis. Now let us look at the pi pi star interactions. So pi pi star interactions will be sideways interaction of these lobes. So for example, if I have pz interacting with pz, and I have positive phase interacting with positive phase, negative interacting with negative, then this would be called as pi interaction. Again, the S will be greater than 0 here, because this is bonding interaction. And now if you have, I can write here S greater than 0 or bonding, this will lead to pi bond, this will lead to sigma bond. Now if you have opposite phases of the two orbitals interacting, then you have positive, negative, negative, positive. This will be called as pi star. S will be less than 0, this will be antibonding, right? So now if we see this, if we now run a C2 through this will be antisymmetric. Antisymmetric, that is the character under C2 operation will give you a negative sign, -1 with respect to C2. And if we say sigma V, which is coplanar with the nodal plane, coplanar with nodal plane. So if you draw C2 versus sigma V, this C2 and sigma V, the sigma V will be coplanar with nodal plane, and this will be antisymmetric. So that is the character under these two symmetry operations will be -1. So we know what is antisymmetric, what is symmetric with respect to a given symmetry operation. Now let us also look at non-bonding interaction, for which S will be equal to 0. So this is just again a balloon representation example. So let's say if I have p orbital oriented like this and s orbital oriented like this, so this will be positive, positive, and positive, negative. So there is no change in electron density. So this will give you S equal to 0 or non-bonding interaction. Similarly, you can also have between two p orbitals like this way. So here also it is positive, positive, and positive, negative interaction, which will cancel out each other, and this will be called as non-bonding interaction. Let's also consider d orbitals overlapping form interacting with d orbitals. This is mostly seen in case of metal-metal complexes. Let's say if we have sorry for the bad drawing. So let's say if this is my d orbital, and on top of that I have another d orbital with same lobes, something like this. Now those will also have same signs. Then this will be called as delta, and if you have opposite signs, negative, negative, positive, positive, and you have, instead of positive here, you will now have negative of black, positive of black, positive, and negative. So this will be called as delta star interaction. Okay, so these are typically seen in metal-metal bonding. So, and these are symmetric with respect to C2 and antisymmetric with respect to C4. So, and the C2 is basically collinear with the z-axis. Z-axis is coming out of the plane of the board. So for example, this one is dx square minus y square, dx square minus y square interacting with the same thing. We can also have dxy interacting with dxy and so on. All right, so this gives you a brief introduction of what is chemical bonding. In next lecture we will take up different theories, for example valence bond theory and molecular orbital MO theory. So we'll see how symmetry and group theory rules and symmetry adapted linear combinations can be used to describe the wave functions in case of both of these theories. That is all for today. So see you in next class. Thank you.